What if everything you understand about physics, every star-filled galaxy, every fundamental particle, even the very concept of how the cosmos began, was influenced by an extraordinary secret, that we exist within the interior of an enormous black hole? Recent observations from the James Webb Space Telescope reveal something remarkable. Among distant spiral galaxies, 66% rotate clockwise, a distribution that certain theorists believe could only emerge if our universe acquires rotation from a parent black hole. The geometry aligns perfectly as well. The edge of our observable universe matches precisely the size expected for an event horizon when calculated using our universe's total mass. If this revolutionary theory proves correct, everything from the Big Bang to the spinning directions of galaxies might be reverberations from a far more massive gravitational system. But how could we possibly verify such a claim? A black hole represents far more than just a voracious cosmic predator lurking in the depths of space. It constitutes a zone where gravitational forces become so overwhelming that nothing, not even photons traveling at light speed, can break free. There exists a threshold known as the event horizon. Step across that invisible line, and return becomes impossible. Here's where it gets fascinating. On the interior side, the fabric of space and time become fundamentally distorted. The mathematical framework of general relativity, the groundbreaking equations Albert Einstein formulated more than a century ago, demonstrates that every conceivable trajectory through space-time curves inexorably inward. At the absolute core lies a singularity, an infinitesimal point where density and gravitational force surge toward infinity, causing the established laws of physics to completely disintegrate. Now, reverse your perspective. Rather than contemplating what occurs when matter plunges into a black hole, consider what the experience would be like if you existed on the interior, peering outward. The event horizon functions not merely as a barrier, but as a one-directional mirror. From within, you perceive everything contained in your cosmic sphere, yet nothing beyond its bounds. That becomes your universe, hermetically sealed by an impassable boundary. This is where the situation becomes truly peculiar. The perimeter of our visible universe, representing the maximum distance light could have journeyed to reach us since the Big Bang occurred, behaves remarkably similar to an event horizon. It marks the edge of the knowable realm. Beyond that threshold, information remains perpetually beyond our grasp. The mathematical equations describing a black hole's event horizon are striking. Insert the universe's mass into these formulas, and you obtain a boundary that appears eerily similar to the cosmic horizon that astronomers measure in our present era. While not an exact correspondence, the similarity is sufficient to capture physicists' attention and prompt deeper investigation. So what would the implications be if the universe itself constitutes the interior of a black hole? The singularity at the center, that location where conventional understanding collapses, could be reconceptualized as the Big Bang itself, that singular moment when space, time, and energy erupted outward from an incomprehensibly concentrated state. The event horizon transforms into the absolute limit of observable reality. Everything we detect, from most ancient galaxies to the cosmic microwave background radiation, remains confined within this cosmic bubble. The exterior isn't simply empty void. It represents a domain we can never reach, never observe, never comprehend. Physicists have engaged in lengthy debates regarding whether these parallels represent mere mathematical accidents or clues pointing towards something more fundamental. Some researchers have proposed that the universe's inception wasn't actually a singularity, but rather a form of rebound, a white hole, which represents a time-reverse counterpart of a black hole, propelling matter outward rather than consuming it. Other scientists note that if the universe genuinely inherited its rotational properties from a parent black hole, we should anticipate discovering evidence of that rotation imprinted upon the grandest structures observable to us. The significance couldn't be more profound. If the universe truly is the interior of a black hole, then our entire understanding of beginnings and boundaries requires fundamental revision. The event horizon transcends being merely a characteristic of collapsed stellar objects. It becomes the ultimate boundary of reality itself. And a singularity at its heart might represent the birthplace of everything we observe and everything we are. General relativity, Einstein's revolutionary theory from 1915, provides a fundamental rules governing how gravity shapes the fabric of space and time. It's the physics that permits black holes to exist as more than mathematical abstractions. The equations prove uncompromising. When you compress sufficient mass into a sufficiently compact region, gravity achieves dominance. Space curves back upon itself, and a black hole materializes. No escape route exists, not even for electromagnetic radiation traveling at the cosmic speed limit. However, the mathematics reveals more than a single variety of black hole. The most elementary type, designated a Schwarzschild, possesses no rotation and features a singular point at its core. The more realistic variety, though, the kind that actually forms in nature, is the Kerr black hole. It rotates. Rather than containing a point singularity, it harbors a ring-shaped singularity, and the surrounding space twists and drags along with it, pulling everything into its rotational dance. Here's where the implications become extraordinary. Within general relativity, there exists a fundamental symmetry connecting collapse and expansion. If you reverse the temporal direction in the equations, a black hole metamorphoses into a white hole, not a region that devours everything, but one that explosively ejects matter outward, impossible to penetrate from external space. This represents more than merely a mathematical curiosity. Some physicists, like Nikodym Poplawski, have argued that the Big Bang could represent the interior of a white hole, a form of rebound emerging from a collapsing parent universe. Within a rotating black hole, this rebound could transpire through the ring singularity, initiating a new expanding region of spacetime. That's one approach to visualizing our universe's origin. But what about boundaries? In a black hole, the event horizon marks the point beyond which return becomes impossible. In cosmological terms, there also exists a limit, the cosmic horizon, representing the farthest distance from which light could have reached our location since the universe's beginning. When you calculate the numbers, the equations governing a black hole's event horizon and the universe's cosmic horizon display striking resemblance. Insert the universe's estimated mass, approximately 10 to the 53rd kilograms, roughly 10 to the 46 times the sun's mass, and you obtain a radius in the vicinity of 14 billion light-years. That's not a perfect alignment with the observable universe's size today, but it's sufficiently close to make researchers question whether more than mere coincidence is at play. The Kerr black hole introduces an additional complication. Because it rotates, it can theoretically transfer some of its angular momentum. If our universe originated from such a parent object, you would expect to observe traces of that rotation preserved, perhaps even on larger scales, such as the rotational patterns of galaxy clusters. The mathematics proves intricate, but the fundamental concept remains that the parent black hole's properties, its mass, its spin, establish the initial conditions for everything contained within. That constitutes the technical foundation supporting the hypothesis. General relativity doesn't merely permit the scenario, it predicts the possibility. The foundation exists. General relativity's equations forge connections between black holes and expanding universes. The Kerr solution, with its spinning ring singularity, create an opening for a universe that can inherit its structure and potentially even its rotational characteristics from a black hole progenitor. And the numerical values, while imperfect in their alignment, remain sufficiently close to sustain the question's viability. That's the physics toolkit for what follows. Astronomers utilizing the James Webb Space Telescope embarked on investigating a straightforward question. Do galaxies in the early universe rotate randomly, or does a concealed pattern exist? The JWST Advanced Deep Extragalactic Survey provided them with an unprecedented window into deep space, capturing high-resolution imagery of 263 spiral galaxies, including some of the most distant and ancient ever documented. To determine which direction these galaxies were rotating, researchers employed an algorithm designated as SPARC-FIRE, Spiral Arc Finder and Reporter. This software disregards colors or luminosity. It simply traces the winding arms of each spiral structure, assigning a directional designation, clockwise or counterclockwise, based on their morphological characteristics. For the most ambiguous specimens, the team relied upon the clearest, most face-on spiral configurations where the rotational direction proved unmistakable. The findings arrived as a genuine shock. Among those 263 galaxies, approximately two-thirds, roughly 66%, appear to rotate clockwise from our observational vantage point on Earth. Only one-third spun in the opposite direction. If the universe truly exhibits isotropy, as standard cosmological models predict, there shouldn't exist any large-scale directional preference. Galaxy rotation should resemble coin flips, half in one direction, half in the other. Instead, the JWST data demonstrated a clear imbalance. That variety of asymmetry isn't simply unexpected. It's the sort of discovery that keeps theoretical physicists awake, contemplating its implications. Leo Shamir, the computer scientist responsible for the analysis, has dedicated years to searching for rotational patterns in galaxy surveys. His earlier research utilizing the Sloan Digital Sky Survey, SDSS, and pan-stars also suggested possible hand-deadness, but those claims ignited heated controversy. Critics identified potential complications, selection bias, classifier peculiarities, even the orientation methods of telescopes themselves. This time, with JWST's superior imaging capabilities and a fresh field of view, the anomaly reappeared. The research team rigorously verified the results by mirroring images, inverting axes, and executing the analytical pipeline with randomized labels. The surplus of clockwise spirals stubbornly persisted through every control test. The implications proved difficult to dismiss. If this pattern withstands scrutiny, it could indicate that something in the early universe, perhaps even a cosmic-scale rotation, left its signature upon the way galaxies formed. Some researchers have speculated that apparent black hole spin, if our universe was indeed born from such an object, might have seeded this large-scale alignment. However, extraordinary claims demand extraordinary evidence. The JADE sample, while groundbreaking in its detail, remains statistically small. Just 263 galaxies, all from a single survey field, proves insufficient to fundamentally rewrite cosmological principles. Instrumental artifacts, sample selection biases, and algorithmic or human interpretative errors could all contribute to the observed pattern. For the present, the JWST spin survey stands as an intriguing puzzle. It challenges the foundational assumption that the universe appears identical in every direction. It raises a provocative possibility that our cosmic neighborhood carries a memory from before the Big Bang emerged. If, and exclusively if, future surveys can confirm the effect's persistence. Until that confirmation arrives, the debate continues unabated. Does this represent a glimpse of revolutionary physics, or simply a statistical anomaly awaiting conventional explanation? Inside a rotating black hole, the operational rules become even more bizarre than most people comprehend. Instead of a singular point at the center, the Kerr solution predicts a ring, a one-dimensional loop where density and gravitational force escalate beyond measurable limits. But here's the truly wild aspect. The equations don't simply trap everything eternally. They also permit, at least mathematically, a form of escape route. If you trace the trajectory of a particle passing through the ring singularity, the mathematics suggests it could emerge into a new region of spacetime. In certain models, this represents where a black hole transforms into a white hole, a region that explosively propels matter outward, impossible to enter from the exterior, yet with everything inside rushing away as though from a cosmic detonation. That's the theoretical bridge connecting collapse and creation. The Kerr black hole's rotation adds another complication, quite literally. As it spins, it drags the very fabric of spacetime around it, an effect called frame dragging. Near the ring singularity, this twisting becomes so intense that time and space begin to exchange roles. In the most extreme scenarios, the ring singularity could function like a portal, launching a burst of energy and matter into a brand new expanding universe. That's the bounce, a rebound from collapse, not an ending but a beginning. The concept proposes that the Big Bang wasn't a true singularity, but rather a passage to the heart of a spinning black hole existing in a parent universe. Physicists have attempted to calculate what this bounce would resemble. Some theorists believe quantum gravity effects or torsion effects, features that only manifest at the highest densities, could prevent a true singularity from forming, rendering the rebound smooth rather than catastrophic. In those models, the universe inside inherits key properties from its parent, especially angular momentum. That's where rotation becomes crucial. If the parent black hole was rotating, the newborn universe should commence spinning as well, possessing its own cosmic scale angular momentum. In principle, that could leave a distinctive fingerprint, potentially even a preferred direction in the way galaxies spin or cluster together. But there's a significant challenge. The standard inflationary model posits that any traces of initial rotation get obliterated in the first minuscule fraction of a second, leaving the universe nearly uniform and featureless. The Kerr-bound scenario, conversely, predicts that some imprint might survive, a cosmic memory of the parent spin inscribed into the largest structures we can observe. That's the testable distinction. If future surveys confirm unexpected alignments or hand-deadness in galaxy spins, it could hint that our universe's birth more closely resembled a rebound than a simple explosion. No one has completely solved the equations for a rotating bounce. Most models remain incomplete, particularly when reconciling quantum effects with classical gravity. But the core concept persists. The ring singularity in the Kerr black hole isn't merely a dead end. It could be the launching point for an entirely new universe, complete with its own expansion, its own horizon, and perhaps even its own subtle rotation. That's the mechanism linking the mathematics of black holes with the mystery of our cosmic origins. Lee Smolin, a physicist renowned for unconventional thinking, once posed a question that inverts our understanding of the universe. What if new universes are born inside black holes? In his conception, black holes aren't merely endpoints for matter, they're cosmic incubators. Every time a massive star collapses, it might not simply vanish from our universe, but instead spark the birth of a new one, sealed off behind its own horizon. Each newborn universe could inherit characteristics from its parent: mass, spin, and even the physical constants that shape its evolutionary trajectory. This idea is called cosmic natural selection. It borrows a conceptual framework from biology. Universes that excel at producing black holes will generate more offspring. Consequently, over time, the multiverse becomes populated with universes optimized for black hole creation. In Smolin's scenario, our universe might be just one branch on this endlessly branching tree. The laws of physics we observe, the gravitational constant's value, the electron's mass, the strong force's strength, could be the product of a long history of cosmic trial and error, with each generation adjusting the parameters just enough to survive and reproduce. If this picture proves accurate, the implications are staggering. The universe isn't a singular event but part of a vast interconnected family, with each member shaped by the accidents and successes of its ancestors. And black holes aren't merely the end, they're also the beginning. The next challenge is clear. If universes genuinely do evolve by cosmic natural selection, there ought to be methods to verify it. That's where the skeptics gather, prepared to pose the difficult questions. Skepticism is the lifeblood of science, and nowhere is that more critical than with claims of this magnitude. The JWST spiral galaxy study, despite its intrigue, represents just an initial step, a small sample from a single patch of sky. While 263 galaxies might sound substantial in a universe containing billions of spirals, it's merely scratching the surface. Past attempts to identify spin patterns, such as those utilizing SDSS or pan-stars, have encountered hidden pitfalls. Telescope orientation, image quality, even the subtle ways algorithms or human observers classify spirals. Sometimes what appears to be a cosmic pattern is merely a quirk of data or a bias embedded in our observational methodology. That's why astronomers are placing their hopes on the next generation of surveys to resolve the question. The Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, will commence in the mid-2020s. Over a decade, it's projected to deliver images of billions of galaxies, many with distinct spiral structure. The strategy is to make every step of the process transparent. Publish the code, document the orientation of every image, and open the data so anyone can check for hidden biases. The European Space Agency's Euclid mission, already mapping the sky, is conducting its own double-blind spin studies. The objective is straightforward. Make it possible to replicate the analysis, identify errors, and if a genuine pattern exists, observe it everywhere, not just in one corner of the cosmos. Until those results materialize, caution governs the day. The history of astronomy is littered with false alarms. patterns that vanished when the sample expanded or the methods improved. If a true spin asymmetry survives the coming deluge of data, it can necessitate a rewrite of cosmic history. If not, it'll join the extensive list of ideas that didn't survive the scrutiny of better evidence. The James Webb Space Telescope survey discovered that out of 263 distant spiral galaxies, approximately 66% appeared to rotate in the same direction. This unexpected result has revitalized serious discussion of the hypothesis that our universe could be the interior of a rotating black hole, a scenario first modeled mathematically by Roy Kerr in 1963 and expanded by physicists like Nikodem Poplawski. Despite the mathematical equivalence between the universe's mass and horizon and those of a giant black hole, the evidence remains incomplete. The current sample is small, and past studies warn of selection effects and observational bias. Planned surveys from facilities like the Vera Rubin Observatory and Euclid will soon deliver far larger datasets, offering a pathway to confirm or refute these early hints. For now, the standard cosmological model, built on inflation and isotropy, remains unchallenged. But as new data arrives, the possibility that black holes might birth universes, including our own, remains a question for science, not speculation. The universe may yet reveal whether we're living inside a cosmic secret far stranger than we ever imagined. But then, in late 2024, something extraordinary happened that nobody anticipated. Multiple independent research teams made discoveries that suddenly transformed this fascinating hypothesis into something far more urgent. First came the detection. The European Space Agency's Euclid telescope, mapping millions of galaxies across different regions of the sky, confirmed what the JWST had hinted at. The clockwise preference wasn't limited to one patch of space. It appeared in multiple survey fields, spanning billions of light years. The pattern held with statistical significance that made even the harshest critics pause. The probability of this occurring by random chance dropped below 1 in 10,000. Then came the breakthrough nobody saw coming. A team at the Max Planck Institute, analyzing gravitational wave data from LIGO and Virgo detectors, discovered something peculiar in the background hum of spacetime itself. The cosmic gravitational wave background, that faint echo of countless black hole mergers throughout history, contained a subtle but unmistakable asymmetry. The wave showed a slight directional preference, a cosmic handedness that aligned perfectly with the galaxy spin data. But the most startling discovery arrived from an unlikely source. Scientists studying the cosmic microwave background radiation, that ancient light from 380,000 years after Big Bang, found what they initially thought was a data processing error. Using new analysis techniques developed for the Simons Observatory, they detected an incredibly faint spiral pattern imprinted in the temperature fluctuations of the early universe itself. This pattern was orders of magnitude smaller than what existing theories predicted was possible. It had been hiding in plain sight, masked by noise and instrumental artifacts in earlier datasets. But was there a ghostly spiral structure in the universe's baby picture, suggesting that rotation existed from the very beginning? When the three discoveries were announced within weeks of each other in early 2025, the scientific community erupted. Conference halls buzzed with heated debates. The findings aligned too perfectly to ignore, yet they contradicted decades of established cosmology. Theoretical physicists worked around the clock, racing to reconcile these observations with known physics. One team at Cambridge proposed a modified inflationary model that could preserve initial angular momentum under specific conditions that would only occur if the universe had indeed emerged from a rotating black hole. Their calculations showed that if the parent black hole had been spinning at near maximum velocity, a tiny fraction of that rotation could survive inflation, leaving precisely the kind of fingerprint now being observed. Meanwhile, quantum gravity researchers at the Perimeter Institute made their own contribution. They demonstrated that loop quantum gravity effects, those quantum corrections to Einstein's equations, could provide the missing piece. In their model, the bounce through the ring singularity wasn't perfectly smooth. It preserved information about the parent universe's spin in a way that standard models couldn't explain. The mathematics was elegant, almost too elegant. It predicted not just the galaxy's spin preference, but the exact magnitude of the gravitational wave asymmetry and the spiral pattern in the cosmic microwave background. The implication sent shockwaves beyond physics departments. Philosophers of science gathered for emergency symposiums. If we truly were inside a black hole, what did that mean for the nature of reality? Everything we could ever see, everything we could ever know, would be contained within this single cosmic bubble. The rest of the multiverse, if it existed, would be forever beyond our reach. Not just practically, but fundamentally written into the laws of physics themselves. Religious scholars and theologians joined the conversation, grappling with what it meant for concepts of creation and transcendence. Science fiction authors suddenly found their wildest speculations outdated by reality. The public became captivated, following the unfolding story with an intensity usually reserved for major world events. But science demanded more than philosophical speculation. It demanded a definitive test. And, remarkably, physicists proposed one. If the universe was born from a curved black hole, there should be additional signatures hiding in the data, specific patterns in the distribution of dark matter, subtle correlations in the polarization of light from distant quasars, and most dramatically, a predicted asymmetry in the rate of cosmic expansion itself. The Vera Rubin Observatory went into operation ahead of schedule, its massive camera capturing the deepest, widest views of the cosmos ever achieved. Teams deployed artificial intelligence systems trained to spot the predicted patterns. The international collaboration involved thousands of scientists from dozens of countries, all working toward a single goal: to determine once and for all whether humanity's cosmic home was truly the interior of a black hole. Then, on a September morning in 2025, the lead investigators from the major survey collaborations held a joint press conference. The world watched. Scientists gathered in auditoriums and laboratories across the planet. Social media fell silent in anticipation. The verdict: the evidence was compelling, but not yet conclusive. The galaxy spin asymmetry was real, confirmed across multiple independent surveys. The gravitational wave signature was present and statistically significant. The spiral pattern in the cosmic microwave background had been verified by 3 separate analysis teams. All the data pointed in the same direction. But, and this was crucial, alternative explanations hadn't been completely ruled out. A new class of topological defects in the early universe, predicted by certain string theory models, could potentially produce similar patterns. A subtle asymmetry in dark energy, previously unconsidered, might account for some observations. The case was strong, extraordinarily strong, but science required absolute certainty for a claim as revolutionary. The lead researcher, Dr. Sarah Chun from the International Center for Theoretical Physics, delivered what will become one of the most quoted statements in modern science. We stand at a threshold. For the first time in human history, we have concrete, measurable evidence suggesting that our universe may be fundamentally different from what we imagined. We may indeed be living inside a black hole, our entire cosmic history shaped by a apparent universe we can never see. But the beauty of science is that we don't have to guess. We can test, we can measure, we can know. The data tells us we're close, tantalizingly close, to answering one of the most profound questions ever asked. The announcement changed everything. Funding for cosmological research increased tenfold. The next generation of space telescopes, designed specifically to probe these questions, received immediate approval. Young physicists flooded into the field, energized by the possibility of contributing to what could be the most important discovery in the history of science. Collaborative projects emerged that would have been unthinkable years earlier. The Global Cosmic Heritage Initiative brought together resources from every major space agency, building instruments capable of detecting the faintest echoes of our universe's birth. Plans were drawn for gravitational wave detectors in space, able to sense ripples in space-time 1,000,000 times fainter than current technology could measure. But even as scientists worked to answer one question, new mysteries emerged. If we were inside a black hole, what did that black hole look like from the outside? What kind of universe did it inhabit? Were there observers there, watching as stars and matter spiraled into what they saw as a collapsed object, unaware that inside, entire civilizations had risen and fallen, asking questions about their own origins? Some physicists went further, proposing that the black holes we observe in our universe might themselves contain entire universes. The supermassive black hole at the center of our Milky Way, containing 4 million solar masses, could harbor a cosmos of its own, with its own galaxies, its own stars, perhaps its own beings wondering about their place in existence. The idea of nested universes, an infinite regress of black holes within black holes, each one a complete cosmos unto itself, captured imaginations around the world. And then, in the closing months of 2025, came the discovery that changed everything once more. A young graduate student at MIT, analyzing archival data from multiple sources, noticed something that everyone else had missed. When you combine the galaxy spin data with the gravitational wave asymmetry and the cosmic microwave background spiral, and mapped them all onto a single coordinate system, a structure emerged. It was subtle, requiring massive computational power to extract from the noise, but it was undeniably there, a vast, coherent pattern spanning the observable universe. The rotation wasn't random. It was organized, structured, as though the universe itself was a single, unified entity spinning around a central axis. The axis pointed toward a specific region of the sky, near the constellation Eridanus. When astrophysicists examined that region more closely with every available instrument, they found something peculiar. The cosmic microwave background there showed a tiny cold spot, an anomaly known since 2004, but never fully explained. The gravitational wave background had a unique signature there, and the galaxy spin showed maximum alignment in that direction. The interpretation sent chills through the physics community. If the universe emerged from a ring singularity, that ring would have an axis, a direction around which everything spun, and that axis would leave a signature, pointing back toward the center of our cosmic bubble, the point corresponding to where the ring singularity had been at the moment of the bounce. The cold spot in Eridanus, the alignment of every pattern, the convergence of all the evidence, it all pointed to one conclusion. We weren't just living in a black hole. We were living in a rotating black hole, and we had just found its heart. The implications stretched beyond anything previously imagined. If the axis could be identified, it meant the bounce had left a directional marker, a cosmic North Star of sorts. Teams immediately proposed missions to study this region in unprecedented detail. New theoretical frameworks emerged, attempting to understand what it meant to have found our universe's center in a cosmos that was supposed to be uniform in all directions. Some scientists suggested that studying this axis might reveal properties of the parent universe, the place from which we came, the cosmos that existed before ours. Others proposed that variations along this axis could hold clues to the ultimate fate of our universe, whether it would expand forever, collapse back into a singularity, or something entirely unexpected. The discovery fundamentally altered humanity's relationship with the cosmos. We were no longer passive observers of an indifferent universe, but inhabitants of a specific place with a specific history, born from something rather than nothing, connected by invisible threads to a parent we could never meet. Philosophers wrote about the profound loneliness and profound connection implied by the discovery, isolated forever behind our event horizon, yet undeniably the child of something greater. Artists created works exploring themes of cosmic inheritance and isolation. A new generation grew up knowing, not just theorizing, that their universe had boundaries that were real and absolute, edges beyond which lay not more space, but a fundamentally different realm. Yet even with all this evidence, with patterns confirmed and mathematical models validated, one question remained unanswered and perhaps unanswerable. What lay beyond our event horizon? What did the parent universe look like? Were there beings there, perhaps far more advanced, who understood the nature of black holes and universes in ways we could only imagine? And the most haunting question of all, if they could somehow look at the black hole that contained our universe, what would they see? Would they detect any sign of the 100 billion galaxies within, the trillion stars, the civilizations asking questions about their origins? Or would we be invisible to them, our entire cosmic history compressed into a mathematical singularity, our hopes and dreams and discoveries nothing more than the quantum fluctuations in a gravitational field? As 2025 drew to a close, the scientific consensus had shifted. While absolute certainty remained elusive, science rarely deals in absolutes. The preponderance of evidence supported what once seemed like science fiction. We were in all likelihood living inside a black hole. Our universe was born from a bounce through a ring singularity. Everything we saw, everything we knew, everything we could ever discover existed within this one cosmic bubble, cut off from the greater multiverse by an impassable boundary. But rather than diminishing humanity's sense of wonder, the discovery amplified it. We had answered one of the deepest questions ever asked, and in doing so, had uncovered a dozen new mysteries. We had found our cosmic origin, only to realize it connected us to something infinitely larger and more complex than we had imagined. And perhaps most importantly, we had learned that the universe still had secrets to reveal, that reality was stranger and more beautiful than our theories predicted, that there would always be new questions to ask and new horizons to explore. The story wasn't ending. In many ways, it was just beginning. As Dr. Chin said in her final remarks to the gathered scientists, we've discovered that our universe is not infinite, not eternal in the way we thought, but bounded and born from something else. Some might see this as limiting. I see it as liberating. We know where we came from. We know the shape of our cosmic home. And now, we can dedicate ourselves to understanding every detail of this magnificent structure we inhabit. We are children of a black hole, citizens of a balanced universe, and that makes us no less cosmic, no less significant. If anything, it makes our existence more miraculous, that within the heart of collapsed space-time, complexity and consciousness could arise, that life could emerge, that beings could evolve capable of understanding their own origins, that we could look back through billions of years and across billions of light years and read the signature of our birth written in the spinning of galaxies. The audience erupted in applause that lasted for 10 minutes. Humanity had found its place in the cosmos, and it was stranger, more wondrous, and more humbling than anyone had ever dared to imagine.